What if the forest you were standing in could tell you exactly which direction was north? Without a compass, without a phone, without a single piece of technology, using nothing but the angle of the leaves on a plant that has been doing this reliably for millions of years? And what if the Vikings crossed the entire North Atlantic Ocean, in fog so thick they could not see the sun, using a crystal they held up to the sky? A technique so effective that modern physicists tested it in 2013 and confirmed it works to within a single degree of accuracy? Both of these things are real. Both of them were documented and used by people who navigated the world long before GPS existed. And both of them are things you can learn today, test in your backyard this week, and use for the rest of your life. Stick with me, because the Sunstone section is going to change how you look at a piece of calcite, and the compass plant has been growing in fields and roadsides across North America your entire life without anyone telling you what it can do. Start with the compass plant, because this is the one that most people have walked past 1,000 times without knowing what they were looking at. Silphium laciniatum, the prairie compass plant. A tall, dramatic wildflower native to the grasslands of North America, it grows 3 to 8 feet tall, produces yellow daisy-like flowers at the top of a rough, hairy stem, and has deeply cut, irregular leaves that look almost prehistoric in their shape. It grows across the tall grass prairie region from the Dakotas down through Nebraska, Kansas, Oklahoma, and into Texas, and in disturbed meadows, roadsides, and open fields throughout much of the eastern and central United States. Native American peoples across the plains relied on it for generations. Early European settlers gave it its common name, not because someone decided to call it that, but because of something they observed happening consistently, repeatedly, and with enough reliability to name the plant after it. If you're out on open prairie and need direction, one of the best natural clues is this plant's leaf alignment. The large lower leaves usually grow almost straight up instead of lying flat, and they tend to line up north to south. That means the broad faces of the leaves usually look east and west, while the thin edges point north and south. To use it, don't look at just one leaf. Check several of the big lower leaves and find the direction most of them are lining up. That gives you a solid north-south line you can use to orient yourself and figure out which way to move. The best place to check is on mature plants in open, sunny prairie, because that's where the alignment shows up most clearly. It's a smart natural compass, and when you read several leaves together, it can be a very helpful way to get your bearings. The basal leaves, the large lower leaves at the base of the plant, orient themselves on a north-south axis. The flat face of the leaf points east and west. The edge of the leaf points north and south. This is not occasional or approximate. In open conditions with full sun exposure, the orientation is consistent and reliable enough that multiple independent observers in different centuries documented it independently and reached the same conclusion. This plant tells you where north is. Abraham Lincoln reportedly used compass plants to navigate while surveying land in Illinois in his early career. The botanist John Muir documented it. Multiple 19th century natural history accounts confirm the same observation across different locations and different observers. The mechanism is well understood. The leaves orient to minimize direct midday sun exposure, the intense overhead radiation of noon, while maximizing the gentler morning and evening light that comes from the east and west. Because the sun's most intense overhead position is due south in the northern hemisphere, leaves that edge on to that south position, pointing their flat face east and west, receive less heat stress and survive better. Over evolutionary time, plants in exposed, high-sun prairie environments that oriented this way had a survival advantage, and that trait became dominant. The plant did not decide to be a compass. Physics and selection did it for the plant. And the result is a living directional indicator that has been growing in North American grasslands for millions of years. To use it, find a compass plant in an open area away from buildings, tree shade, or anything that might have disrupted its light exposure. Look at the basal leaves. The big lower ones, not the ones at the top of the stem. Stand back and observe which direction their flat faces point. If that direction is east-west, the edges of those same leaves are pointing north-south. Cross-reference with a few plants in the same area if possible. In good conditions, with fully established plants in open sun, this method is accurate to within 10 to 20 degrees. Not a precision instrument, but a reliable directional indicator that requires no tools, no charge, and no signal. Other plants in the same family and others share similar tendencies. Wild lettuce, Lactuca cereola, a common roadside weed found across Europe, North America, and Asia, does the same thing. Its leaves orient vertically with their faces pointing east and west and their edges pointing north and south. It is so consistent in this behavior that it is also called compass plant in parts of Europe. Prickly lettuce, its close relative, behaves identically. These plants are found on disturbed roadsides, waste ground, agricultural edges, and garden margins almost everywhere in the temperate world. chances are one is within walking distance of where you are right now. Now the Sunstone. And this is the one that sounds like mythology until you understand the physics, and then it sounds like something that should be taught in every navigation class ever. The Viking sagas, the medieval Icelandic texts that document Norse history, mythology, and navigation, make repeated reference to a stone called a solarstein, a sunstone, held up to the sky on overcast days to locate the sun and establish direction for open ocean navigation. For a long time, scholars debated whether this was literal or metaphorical. Then, in 2011, a piece of calcite crystal was found in the wreck of an Elizabethan warship sunk in 1592 near the Channel Islands. It was positioned among navigational instruments. And in 2013, a team of researchers from the University of Rennes published a study in the Proceedings of the Royal Society demonstrating experimentally that Iceland's Spar, a transparent variety of calcite, can locate the position of the sun on overcast days to within a single degree of accuracy. The Sunstone was not mythology. It was a precision optical instrument made of a naturally occurring crystal that the Vikings found, understood, and used to cross the North Atlantic. Here is the physics. Calcite is a naturally occurring crystalline form of calcium carbonate that has a property called birefringence, also called double refraction. When light passes through a birefringent crystal, it splits into two beams that travel at slightly different speeds and emerge polarized at 90 degrees to each other. Sunlight, even on an overcast day, is partially polarized. The light that scatters through cloud and atmosphere retains directional information about where the sun is, even when the sun itself is invisible. When you look through a piece of Iceland spar calcite at the sky and rotate it slowly, the two images of whatever you're looking at change in brightness relative to each other. When the two images are equally bright, you are looking at right angles to the plane of polarization. And when one image is brightest and one is darkest, you are aligned with the polarization axis. That polarization axis points toward the sun, even through clouds, even in twilight, even when the horizon is completely obscured. The Vikings did not know the word polarization. They did not have a theory of electromagnetism. But they observed what the stone did, learned what that meant for direction, and used it to navigate from Norway to Iceland to Greenland to Newfoundland in vessels that the modern world would consider dangerously small for the North Atlantic. The 2013 Rennes study concluded that with practice, a navigator using Iceland Spar can determine solar direction to within approximately 1 degree of accuracy under simulated overcast conditions, comparable to a magnetic compass and in some conditions superior to one, since it is unaffected by magnetic deviation near iron deposits, or in high latitudes where magnetic compass variation becomes significant. Iceland Spar, optical grade calcite, is available from mineral suppliers, rock and gem shops, and Amazon for roughly $5 to $20 per piece depending on size and clarity. It is not rare. It is found in large deposits in Iceland, Mexico, and multiple other locations. To use it correctly, you need a piece clear enough to see through with some transparency. Hold it up toward a bright area of sky on an overcast day. Look through it at a light source, a patch of bright cloud, a diffuse light area. Rotate the crystal slowly. Watch the two images that appear. The point where the two images are of equal brightness is your reference point. The sun's direction is 90 degrees from where you are looking. Practice on partly cloudy days when you can compare your reading to the actual sun position. You will develop a feel for the rotation and the brightness differential within a few attempts. The more practice you have before you need it, the more accurate and confident you will be when you do. Two other natural navigation techniques worth knowing that complement these tools. The first is shadow stick navigation, arguably the oldest navigation method in the world. Push a straight stick about 2 to 3 feet long vertically into flat ground in a sunny location. Mark the tip of the shadow with a small stone or a scratch in the dirt. Wait 15 to 20 minutes. Mark the new position of the shadow tip. The line between the first mark and the second mark runs approximately west to east. The first mark is west, the second is east. A line perpendicular to that runs north-south. This works because the shadow moves as the sun moves from east to west across the sky. In the northern hemisphere, the shadow moves from west toward east over the course of the day. The technique is accurate to within a few degrees in most conditions and works anywhere in the world with sufficient direct sunlight. The second is star navigation, specifically Polaris, the North Star, which sits within approximately 1 degree of true north and does not move appreciably as the Earth rotates. Polaris is at the end of the handle of the Little Dipper constellation. To find it reliably when you cannot identify the Little Dipper, locate the Big Dipper, a much more prominent and recognizable pattern. The two stars at the outer edge of the Big Dipper's bowl, farthest from the handle, are called the pointer stars. Draw an imaginary line from the bottom pointer star through the top pointer star and continue that line outward approximately 5 times the distance between those two stars. That line points directly to Polaris. Once you have Polaris, you have north, a fixed point in the sky that has guided navigators across every ocean and every continent for as long as human beings have looked up. It requires a clear night, no cloud cover, and the ability to recognize a handful of stars, a skill that takes one evening to learn and stays with you permanently. What all of this adds up to is something worth sitting with for a moment. The Vikings crossed the North Atlantic, arguably the most difficult ocean passage in the world in terms of weather, fog, and distance from land, without GPS, without a magnetic compass, and without any of the technology we now consider indispensable for navigation. They did it with a crystal, knowledge of stars, an understanding of ocean swells and bird behavior, and a navigation tradition passed down through generations of people who observed the world carefully and built their knowledge into systems that worked. The prairie compass plant oriented its leaves millions of years before the first human noticed that fact. The polarizing properties of calcite existed long before the first Viking sailor held a piece up to a cloudy sky and watched 2 images shift. The shadow moves the same way it has moved since the Earth began rotating. Polaris has been in the same position relative to the North Pole for all of recorded human history. None of this knowledge disappeared, none of it stopped working. It is sitting in fields, in rock shops, in the night sky, and in the physics of light, waiting for anyone who decides to learn it. That's it for me today. I hope you learned a lot, and I'll see you in the next one.